So I'm going to convince you that buried blue carbon is good carbon. So my name's Natasha Barlow and I'm based at the University of Leeds here in the UK. And what do I mean by blue carbon? I now have tech issues. Hold on, press on the screen. There we go. Okay, so blue carbon. Blue carbon is the carbon that's stored in coastal and marine ecosystems. And by that I mean places such as this beautiful salt marsh on the coast of Scotland that I was working at a few weeks ago, and also marine sediments. And they play a key role in the global carbon cycle. And I know there's a few people here who are also interested in this, but for many people this is a kind of new idea. And coastal ecosystems such as salt marshes and seagrass meadows are also thought to play potentially a key role in the climate crisis, offering nature-based solutions to store carbon. We've recently finished a piece of work from a major study here in the UK looking at the amount of carbon that these salt marshes sequester. And actually it's much less than we thought. So we've estimated, doing a nationwide analysis, that they store about 46,000 tonnes of organic carbon every year. Now, that sort of sounds quite a lot, but when you consider that UK salt marshes, which are not the biggest in the world, store in total about 5.2 million tonnes, the amount they sequester annually is really quite small. And therefore, it's really important that we not only think about the ecosystem service that these things potentially actively involve, but also that it's really important to protect the blue carbon already stored and buried in these systems. And if we're to move offshore now, there's recently been a really significant policy and research shift looking at the carbon stored in the top 10 centimetres of seabed sediments. And the reason for that is twofold. One, these are the areas that actively involve life and biological systems that may in turn store carbon, but also these are the depths that are impacted by fishing and trawling. But our research has shown, and my background is not in carbon, my background's in paleo-environmental change, that by focusing on these sediments in the top 10 centimetres, that only contain about 5% of organic carbon, and that's highlighted in this core picture here with the yellow box around it, we're actually ignoring a really significant, deeper buried store of carbon. And these are submarine peatlands. And the carbon content contained within these peats is up to 60%. So this is huge compared to shallow marine sediments or even the carbon that's stored in salt marshes. And we can use geophysical data, which is effectively taking an X-ray of the seabed, to look at the distribution of these different peat layers. Why do these peats exist? Well, actually, many of our continental shelves would have once looked like this. During periods when sea level was lower, following the last ice age, for example, when Britain was once formally connected to Europe, it provided expansive landscapes for terrestrial peatlands to form. And climate warmed, and we had periods of peatland development for about 12,000 to 8,000 years ago. Sea level then rose and flooded and separated Europe from the UK and buried many of these peatlands under the sea. And this is not just unique to the North Sea, but we see submarine peats around many of the continental shelves are exposed during this time. You can see these expansive continental shelves in colours in this map. And through archaeological and paleo sea level research, we know that there are peats preserved in these landscapes. And by the nature of these peats forming in shallow marine settings, or once were terrestrial, they are also settings that are prime for human activity, whether that be offshore wind, telecommunications cables, or mineral extraction. And our research has shown that these submarine peats are incredibly carbon dense. So this is just them compared for their carbon store per unit area against many other globally important carbon stores. And we can see against tropical forests that we do a lot of work to try and preserve, that these submarine peats are far more dense in terms of their carbon content. Even more so when we consider them against shallow marine sediments that have been so much of the focus of recent policy. However, the challenge is that this offshore infrastructure in these shallow marine settings is disturbing potentially this blue carbon store, whether it be through the foundations of offshore wind or through export cables that are required to transfer this energy onshore. And you can see on the right here, this is an example of the trenching that is required to bury these communications cables or export cables. The problem is that by the nature of the formations of these peats that were formed over thousands of years when sea level was lower, that carbon is irrecoverable. We cannot recover that in time for the global net zero 2050 deadlines. It's just impossible, much like if we cut down old growth forests as well. So the disturbance of blue carbon, whether that be in coastal systems such as salt marshes or in these submarine peats that as a paleo sea level scientist I've known about since I was an undergraduate, but that the carbon community has not been considering, risk the release of CO2 into the atmosphere and the oceans. The interesting thing is we actually don't know if that's true. And we have no idea whether that old carbon, if we disturb it, will release carbon and CO2 into the oceans and the atmosphere. We have no idea. And this is an area of research that requires significant investment and work. But it's also important to say that we're required to think about this as a whole system. I have work funded by the offshore industry. I'm very keen that we build wind farms. I'm not saying we don't, but we need to balance the need to develop a green economy whilst also protecting our naturally stored carbon. Thank you.